This is a lesson on heat and calorimetry. For various reasons, what we're going to do is we're not going to consider the heat or the work done in a chemistry lab. For elementary chemistry, we're not going to do things under pressure and worry about expanding gases forcing against the cylinder. It is important that's how your automobile works, but in chemistry, we're not going to be worrying about this. So delta H equals Q, heat is enthalpy at a constant pressure. If the pressure is changing, then all bets are off. But we're going to do things usually at room temp or open containers, which means that atmospheric pressure is not going to be any different. For an example, how much heat or how much energy is required to dissolve 10 grams of how much energy it takes to dissolve 10 grams of sodium hydroxide if 1 mole of sodium hydroxide gives off 800 kilojoules of energy. Okay, this is in moles, this is in grams, so you're going to have to do the mole conversion. I'm given is 10 grams of NaOH, 1 mole, and the molar mass is 40 grams, times, now it's giving off 800, so it's negative 800 kilojoules per mole. Grams cancel, moles cancel, do the math, and you'll get negative 200 kilojoules of energy. So that's working with moles and grams. Calorimetry. Calor, if you take Spanish, you know is heat. So it's the study of measuring heat. Heat capacity. Definitions again. Heat capacity is C, which is the change in heat per change in heat per change in temperature. So how much heat is absorbed or whatever per change in temperature. This is given to you as joules, the labels, joules or kilojoules per degree Celsius is the label on heat capacity. Heat capacity, you'd have to figure out how much energy it takes for each individual. So this is not too useful, except for one case where we have a calorimeter and we're going to have to find out how much energy is absorbed. So unless you're using the same object over and over and over again, the heat capacity is not too useful. More helpful unit would be the specific heat capacity. Specific heat capacity is the energy needed to raise 1 gram of a substance 1 degree Celsius. it's abbreviated C, lowercase c. Now our textbook uses S, some textbooks uses S. So C is equal to heat energy is joules per gram degrees Celsius. This is more useful than just the heat capacity, because if you weigh the object, then you know how much energy is needed. So it's not specific object related, it's general. You can also have a molar heat capacity, which is the energy needed to raise 1 mole of a substance 1 degree Celsius. The grams is replaced with the G, so C, joules, gram, degrees Celsius. I think that's where the S comes from. Maybe the S is for specific heat, or molar heat capacity in the book. I don't know. Moles. I said moles and wrote grams. So let me do that over. S, joules per mole degrees Celsius. At constant pressure calorimetry, we're going to be doing in this course. Example problem. The equation, delta H equals mc delta T. Change in mass times the specific heat times the change in temperature will give you the change in heat. So this is what happens in a calorimeter cup if the pressure is constant. So example of a problem like this would be if 30 grams of iron with a specific heat capacity of 1.2 joules per gram degree Celsius, and that's made up, I have no idea what it is, goes from 21 degrees Celsius to 61 degrees Celsius. How much heat is needed or added or removed? It's going up, so it's going to be added. Substitute into the equation. The mass is 30. The specific heat is 1.2. Change in temperature is 40. Do the math, and you get 144 joules. Now, sometimes in chemistry, they want the answer in kilojoules per mole. Same problem. Well, you know how many joules, and you know how many grams, so you just got to do a couple of conversions. 30 grams, 1 mole, 55.8 for iron. Do the math and you end up with 0.538 moles. 144 joules is 0.144 kilojoules. And you want the answer in kilojoules per mole. 0.144 divided by 0.538 equals 0.268 kilojoules per mole. So it's just conversion problems if you need to. Sometimes they do that, sometimes they don't. Bond calorimetry is used extensively when you produce a gas. So what you do is you keep it underneath a constant volume. The pressure changes, but the volume's not changing, so that's not a factor there. The math is the same. The bond calorimeter is essentially a hand grenade just waiting to go off. It's in a sealed container, and they ignite the sample through electrical wires. So you push a button, they measure out how much energy is increased. Pretty much exactly the same thing as heat, say styrofoam cup calorimetry that we've been doing. The math is the same, the concepts are the same, except you have a sealed container, so the gas is produced, does not change the volume, so there's no work being done. The math is the same, MC delta T, delta H. If there's, remember the equation, heat plus P delta V. If that's zero, then that term's zero, so it's still delta H equals Q. And the Q is still that. No, we are not going to do any bomb calorimetry in a lab. That concludes this lesson on heat and calorimetry.